and chair of the seminar. So today we have a speaker from the University of York, UK, and Jessica Park, and she will be talking about the very interesting result using the D-Wave 2000Q. And the title of the talk is the spatial correlation in the qubit property of the measured and simulated qubit network. So you have the roughly 20-minute talk and 10-minute discussion. Yes, please start.
Perfect. Well, thank you so much for having me, and thank you everyone for coming to listen. As said, I'm Jessica Park. I'm a PhD student at the University of York, working with Susan Annealing, and the PhD is also funded by DSTL. And this is a piece of work that I did, I guess, towards the tail end of last year. And I'll take you through some of the motivations of why I carried out the work, the methodology behind it, the results, and what I'm kind of doing to follow on from this. So I guess most of you probably don't need the introduction to quantum annealing, but just so that we're all on the same page in terms of notation and vocabulary, quantum annealing is a non-universal type of quantum computing, and is most commonly used to find the optimal solution to a problem. It does this by finding the global minimum of an energy landscape that encodes the problem to be solved. And that's in this second term of this quantum annealing equation. Annealing happens over a time frame between 0 and TF, which we typically normalize into a normalized time between 0 and 1. So at t equals 0, this system is in the first, in a mixed state that is represented by the first term of that equation. And then as the annealing schedule progresses, A decreases and B increases. And if that happens slowly enough, the system will move from being in the first term to being in the ground state of the second term, which should encode the solution to our Hamiltonian. This equation also describes a system of qubits and couplers, this second term. And in reality, not all of the couplings can be realized. So this Jij value can only be non-zero where there exists a coupling between qubit I and qubit J. And that's dictated by our network, which is typically a hardware hard-coded thing, unless you decide to do it in simulation. So we decided, partly for simplicity and partly to kind of coexist with the existing research, to model our spin network around the Chimera architecture. So the full chip has just over 2,000 qubits arranged in a 16 by 16 grid of unit cells, each containing 8 qubits. And each qubit is connected both to qubits internal to its own unit cell. So we can see here that qubit 0 is connected to 4, 5, 6, and 7, and also to qubits outside its unit cell, so qubit 16. And obviously, if you extend it to the full 16 by 16 grid, it will have external connections in both directions. What's also interesting is that these qubits, unlike pictured here, aren't just dots, they're superconducting rings, and they are elongated. So qubits 0 to 3 are horizontally aligned qubits, and qubits 4 to 7 are vertically aligned qubits. And that becomes important because we have to remember that these aren't just logical dots on a graph. These are real things affected by real parameters and affected by their fabrication and by their positioning on the graph. So one of the kind of big inspirations for the bit of work that I did was a quantum annealing single qubit assessment paper that was developed by a group at the Los Alamos National Laboratory in the US. And they came about of this because in order to exploit maximum performance from a quantum device, you need to measure the performance of individual qubits and couplings in that device. So they extract 4 parameters: inverse temperature, bias, transverse field gain, and noise. So for each qubit in the system, you get these 4 parameters. And they, in this study, found significant differences in the behavior between qubits that were oriented horizontally to those oriented vertically. And they suggest that this may be to do with inhomogeneity in the fabrication and performance of the chip. So they were kind enough to share their data with me. And so at this point, I would thank them for that and for the advice they gave me as I was kind of progressing through this work. And I kind of took their data and wanted to investigate how the couplings between qubits may affect the correlation in these 4 values between related qubits. So we calculated a Geary-C measure of spatial correlation, which ranges from 0 being perfect positive correlation and increasingly positive values, so C bigger than 1, representing an increasingly negative correlation. A value of 1 means there's no correlation at all. So when calculated over the whole data set, we can see in this left-hand column of the table, everything sits pretty close to 1. There's very little correlation between connected qubits in any of the 4 parameters. However, when we restricted the calculation to just considering either internal or external connections to the unit cell, significant correlation was seen in inverse temperature and transverse field gain parameters. So qubits that are connected within the same unit cell are likely to be negatively correlated in these values, and the qubits connected between unit cells are likely to show positive correlations. It's important to note here as well that there is no physical difference in the design of internal and external connections. They're also constructed of elongated loops of superconducting material. So we'd expect the manufacturing to be the same. So this initially seemed counterintuitive, as you'd expect qubits that are maybe physically closer together to be more related to each other. They might have physically shorter connections and are likely to experience stronger couplings. So looking at this led us to develop the main hypothesis of our work. So we were speculating that the physical length of a connection between adjacent qubits affects the correlation between them and therefore the overall dynamics of the device. So we understand that these are physical qubits, they're not just nodes in a graph, and therefore their physical positioning and how well they're isolated from each other or not isolated from each other will affect the correlation between them. So we designed a simulated qubit network. And again, it's important to remember that this is just a diagram. These are a simulated qubit network. We chose the Chimera architecture because we're inspired by the Los Alamos paper, but this is just a model of a spin network. So in the model we chose, which is on the right-hand side here, we use these 8 qubits, and these represent 3 different connection lengths. You get the internal connection lengths, such as the one between 3 and 7. You get horizontal external connections, such as those between 7 and 15. They represent the longest ones in our network. And we get vertical external connections, such as between 3 and 19. And we simulated 2 different dynamic situations. We have a constant control case, where we weight all the connections equally. We don't care about the length of them. They have the same coupling strength of 1. And then our test case simulates dipole-dipole scaling. So this being a spin network, it's natural to consider interactions that may occur between spins. And dipole-dipole coupling scales as 1 over r cubed, where r is the distance between the spins. So to simulate this qubit network, we have to simulate the time evolution dynamics. So step 1 is we initialize it into a state where the first qubit, in this case, the qubit I labeled 3, is in state 1, so an upspin, and the other qubits are in state 0. We refer to this as an excitation on this node. The system is then evolved through a time window by solving Schrodinger's equation at each time step. This is done here by expanding the state and the eigenvalues of the Hamiltonian. The full methodology can be read in the paper if people are interested. And then we calculate the probability of that excitation being measured at each node using the formula here. This value is typically referred to as the fidelity of that particular node. And again, it should be noted this is a closed system, so that due to the conservation of energy, we only put one excitation in. The sum of all the probabilities across all the nodes have to equal 1 at all time steps. So we then have the fidelities of the nodes for each case are shown in this slide, both the constant weighted case and the dipole weighted case. The trace that begins at 1 for both cases is node 3, because that's where we start the excitation. And in the constant weighted case, we expect the dynamics of the two nodes that are immediately connected to this initial node to behave identically. And this is the case in this figure. We can see fewer traces because nodes 7 and 19, which are the two immediately connected to the initial excitation, behave exactly identically, as we would expect. With the dipole-dipole couplings, we expect nodes 7 and 19 to behave differently. The shorter internal connection gives rise to that larger fidelity peak, so that orange line that you can see. And the longer connection produces a much smaller peak within the considered time window. And this holds for approximately halfway through the time window, and then actually the excitation spreads much further through the network. So we get noticeable peaks from node 19, starting from about 0.2 Tmax, which is the time window. So this network has a high degree of symmetry and a kind of cyclic nature, if you remember the diagram, which means that excitation transfer can come from a number of paths. When you measure fidelity at any particular node, that could have been transferred through any number of clockwise and anti-clockwise steps. All the possible routes the excitation could have taken to end up at that node at that time. And that's what gives this kind of periodic graph with varying frequencies. So as well as considering the overall dynamics, we want to consider the spatial correlations. And we do this at two discrete times. We have the time of the first peak and the time of the maximum peak in the time window. And in the constant case, this is the same point. And in the dipole case, the first peak occurs at node 19, as we saw in the first one, but actually the maximum peak occurs at node 7. So the graphs here are colorized, where node 3, the initial excitation node, is colored in red, and then the fidelities of the other nodes are colorized from kind of that pale blue of little fidelity into a purple and a kind of bright pink color for maximum fidelity. So if we consider the constant coupling case at the first peak and maximum peak in this case, we can see that 7 and 19, again, as we saw, are behaving identically. For the dipole case, although the maximum peak occurs at node 7, as you might expect, the first peak actually occurs at node 19. So although node 19 is peaking sooner, we can see even at this time it has a much lower fidelity. So to better compare this simulation to the Los Alamos data, we wanted to compare the fidelities of connected nodes. So in these figures, each square represents an edge connecting the nodes labeled at its X and Y positions. And the squares are labeled with the length of that connection, just as a reminder, and colorized by the similarity of fidelities in the equation above. If we first look at the left-hand side graphs, which are taken at the first time step of the peak, in the constant case, we expect the length of the connection to have absolutely no effect on the similarity between nodes. Although this is the case in the first row, as we can see, beyond this, the length, we expect the length to have no effect, but actually we're not seeing these kind of equal rows of similarities. We suspect that this is an effect of the fidelity being comprised of all the probabilities of the different routes the excitation could have taken from one node to the other. So although we've labeled the direct coupling length between those two qubits, if you add up all the paths it could have taken, including multiple forward and backward steps, you get a wide variety of lengths. But in the dipole-dipole case, these results are further complicated by changing the connection strength between the nodes. We see no consistent similarity trends between nodes connected via short edges or nodes connected via long edges. And the charts from the dipole-dipole simulation are noticeably different from the constant case. And we can actually see that all of the fidelity in the dipole-dipole case throughout the time window is kind of up in this top left corner. The coupling strength between across the short node is so considerably stronger than the rest. It's actually managing to isolate that fidelity in a small corner of the graph for a considerable length of time. And looking at the difference between the constant case and the dipole-dipole case, we can actually see that you get complex behavior even in what was our test control case. And that is to do with, even in this small network, the complex connectivity that runs between the different nodes in the network. So this study makes 3 conclusions. The first part was our results on the Los Alamos dataset, which shows that real D-wave measurements show qubit spatial correlations. The second conclusion comes from our control case. And like I said, even simple connectivity can cause complex behavior in spin networks. And then our third conclusion is that in the dipole case, length-dependent interactions can localize the dynamics for short periods of time. And when you're considering that you may see these physical effects in real annealers, this would be an effect that you didn't want. Part of having an annealer is that it behaves as a whole chip, and you don't want things isolated to small regions of the chip. So when you put these 3 conclusions together, the combination of these statements means that for researchers and for users of this kind of device, it's not really sufficient to assume heterogeneity in behavior across the chip. To make full and efficient use of these devices, we do need to consider the physical processes that affect individual qubits, and we've got to do more to investigate their interactions. So this kind of further investigation will fall into 3 broad categories in my mind. Firstly, the simulation of larger networks with more connectivity, including modeling existing and hypothetical D-wave chips. Secondly, simulating more physical interactions that could potentially give rise to the unwanted correlations. So we chose dipole-dipole here because it's native to the kind of spin networks that we were looking at, but it's actually a very extreme case, having scaling that scales as 1/r cubed. There are definitely other, probably more realistic coupling strengths that we can look at in this case. And then we can do further tests on real D-wave devices to investigate whether these correlations could be corrected for and even exploited to find better results to real-world problems. There's nothing to say that we need perfect homogeneity in the chip. What we need to do is understand the heterogeneity and potentially exploit this. So hopefully you'll see the results of these further investigations in the coming months and years as I progress through my PhD. Thank you all for listening. I'm happy to take any questions. I think I've sort of kept time.
Okay, thank you very much. Very interesting talk. So now this is good for the question comment. So any other question or comment from audiences? So please, you switch on your microphone and any question, comment? Paul, please. Yes.
Yes, thanks, Jessica. Very nice talk. I've forgotten how to raise my hand on Zoom, so I'm just speaking. But yeah, maybe I missed this in your presentation, but how is R defined? Is it like some physical distance on the chip, or is it just 1 unit per connecting length of coupler?
So in this case, we just took the ratios from the from this model that D-Wave has a module on network X where you can plot these graphs, and we just took the ratios of their standard layout. We kind of didn't want it to be too, I think if we tried to get too close to the physical system, you end up in a difficult position where things aren't points. So the length of things are ambiguous. We just kind of wanted to have a range of lengths that prove the principle that things, because of the quasi-planar nature, this isn't an n-dimensional hypercube. There has to be different lengths in that chip. So just kind of picking some examples that showed that.
Well, I'm still not quite understanding. Sorry. So see if I can think of an example of.
They're just kind of arbitrary from the diagrams shown.
The question, for example, looking at this figure in front of us, is the value of R between, let us say, qubits 5 and 13 the same as the value of R between qubits 10 and 13, or is it different? The 5 and 13 looks really long in this picture. 10 and 13 looks really short.
Yes, yeah. So R changes depending on the length of that coupling.
Okay,
so in this one, we can. Yeah. Okay, yeah. So in these diagrams, the numbers in the squares are the length. That would be R for that length. So between 3 and 7, we've taken 0.13.
I understand. Excellent. And a quick another question. You had J is always positive, is that right? Which corresponds to an antiferromagnetic interaction. I wondered if you'd looked at ferromagnetic interactions and see any difference or much the same sort of behavior. We
haven't yet. We're hoping that in the upcoming research we'll have a kind of wider range, especially ones that kind of more fit the acceptable values of the D-Wave. So I think the current D-Wave model can take J's between -4 and 4 possibly. So being able to replicate that a bit more closely is definitely something we're looking into in the future.
Good, interesting, thank you.
Jessica, can you repeat it again? Jessica, can you hear me?
Yeah.
Paul, it's okay?
Yes, I'm done. Thank you very much. Yes,
okay,
thank you.
Good. So, any other question, comment? Okay, I have a couple of questions. You were very interesting talk. So, first, actually, the very best question, the definition of the correlation. Actually, this is coming from the fidelity, right? And comparing the fidelity as a function of the annealing type, right? For different qubit, right? And then based on the numerical simulation by solving the Schrödinger equation. So this means that this correlation is coming from the quantum mechanical nature, right? So my question is that, okay, this correlation is coming from the quantum mechanical nature or some other classical nature or both. So it's not so clear about the actual physical origin of this correlation. So correlation means that the quantum mechanical correlation or classical correlation.
It's classical correlation in this case.
Classical correlation. Okay, I see. So then another question is that actually that you use actual DF 2000Q to perform the numeric some, right? Did you already try to perform experiment using the DF 2000Q, or you just perform the numerical?
So this is all numerical simulation.
Okay, only numerical simulation. Okay, So I'd like to know about the actual experiment data by Los Alamos. Actually, that they show some correlation between the inside the unit cell and also the correlation between different unit cell. And they show some tendency. So then my question is that actually in Chimera, so there are many unit cell, right? Los Alamos showed the experiment for some of the 4 unit cell, right? So there are another possibility to choose another 4 unit cell here or here or here. So I'd like to know the actual how can I say it's a sample dependence for the this kind of the correlation.
Yeah, so the Los Alamos data set measured the whole chip. They've got individual qubit properties for the whole chip, and it's a really interesting paper, and they've got kind of a heat map of these 4 parameters across the chip.
I see. Great. I see. Okay. Thank you. So and also they already tried to make same experiment for the D-wave advantage, or still not yet.
I've not seen
also the chip dependence. So this an advantage. Yes.
Yeah. So the in the Los Alamos case, I know that they had a 2000Q on site because actually doing this single qubit assessment is really computationally and expensive in terms of how many calls you have to make to the annealer. So I think they were, able to do it on their own hardware. I haven't seen that they've done it on the newer model, but I'm happy to be corrected on that if it's something I've missed. But yeah, one of the things I'm looking at now is kind of extending the spin networks to different architectures, including the Pegasus architecture and the upcoming Zephyr architecture as well.
I see. So okay. So in your numerical simulation, you solve the Schrödinger equation directly, or okay? So then so my question is, if you add the coherence of the spatial in your numerical simulation, so what kind of the behavior can we expect? So I'd like to know the influence of the spatial and the coherence for the correlation in your setup, in your work. So what can you expect? So the correlation is decrease or increase or something? If we the spatial or the coherence. So actually, the actual D-wave machine, the coherence is not so strong. So then I think that the spatial or the coherence also influences the correlation between the qubits. So then
definitely, I think that if we can model kind of other kinds of errors in our spin network, that would be a really useful place to go next. Because also we want to look at kind of next nearest neighbor correlations, because actually as much as when you manufacture these chips, you try and isolate qubits that aren't supposed to be connected, there may well be kind of leakage between qubits that we don't expect, and there'll be this spatial decorrelation, decoherence across the chip. So kind of extending the simulator to put more and more of that in, because ideally you want the qubits to act independently. So we don't necessarily want to see this correlation. We want to kind of see this independent qubits that kind of behave in the same way to the same prompts, I guess, to the same controls.
Okay, thank you. Good. So any question, comment? So we can accept short question. Okay. Okay, if not, so let's thanks to the speaker again. Very great talk, very interesting. So okay, thank you very much. So okay, this is okay. I'd like to close today's INQA seminar. So anyway, so Paul, do you have any announcement for the INQA seminar, INQA conference or something other?
I'd like to apologise for the technical difficulties we had last week at the seminar.
Yes. Yes.
Michael Huang's seminar. Apologies to everyone there. That will be rescheduled. I think it's scheduled on the 31st of October, just speaking off the top of my head. Check the schedule as it comes through. And we return now to weekly seminars after the August break. Thank you very much, Shiro-san, for sharing today. Thank you, Jessica, for giving the presentation. And I think that's all I wanted to say. Thank you very much.
So thank you very much. See you.
Thank you.
Bye. Thank
Bye-bye.
you. Bye.